Okay, so our start of this semester, chapter 14, focuses on solutions. Okay? Solution chemistry is a really important aspect of chemistry. There's like no doubt in my mind that throughout your, just in 1A lab, you were using some solutions in the lab. It turns out that like solids don't really react with one another very well because those molecules and atoms are kind of frozen in place, right? Solution chemistry is a really popular form of chemistry because everything's in this liquid state moving around where there can be interactions between different molecules. I myself was a biochemist. That's what I got my PhD in. I spent 10 years only doing solution chemistry, okay? Us, if you have any interest in biology, we are essentially just bags of solution, right? Our blood is nothing but a solution with a whole bunch of different proteins and fats and sugars and all that other stuff floating around in it. So especially specific to life, solution chemistry is really important. All right, so first thing we got is some terminology here. So first, what do I mean by a solution, right? Let's say that I take some table salt, some sodium chloride, and I dissolve it in water. To create salt water. That salt water that I've created is a solution. Okay? Strictly speaking, a solution is just a homogeneous mixture of different molecules, different compounds. All right? Some other terminology here. Let's say that I take sodium chloride and I dissolve it into water. The sodium chloride in this example is what we call the solute. Okay? And the water that I'm dissolving my solute in, we call the solvent. Okay? So a solute dissolves in a solvent to create a solution. All right, so again, we got some new terminology here. A solute, that's the thing that you're dissolving into your solvent to create your solution. All right, so I have a recipe here for simple syrup, which is the basis of many cocktails, where you take 1 cup of sugar and 1 cup of hot water, and you stir to combine. All right, in this example, in my recipe here, I want you to tell me what my solute is, what my solvent is, and what my solution is. All right, what's my solute? The sugar. And what's my solvent? The water. And then lastly, what's my solution here? The actual simple syrup itself, right? What you get at the end is your solution. Cool. Water is the most common solvent and probably the only solvent that you'll be using at this point in your chemistry career. When you go on to organic chemistry, you'll be introduced to many organic solvents, but typically speaking, at this level, water is the most common one. Okay? All right. So another phrase that we're going to have that we sort of keep in mind that you may have heard is like dissolves like. Okay? This is this just very simple phrase that people have in their mind when they're preparing solutions, and this is sort of a shorthand for the idea that a polar solute will dissolve in a polar solvent and likewise a nonpolar solute will dissolve in a nonpolar solvent. But polar and nonpolar don't mix. Okay? So if you took a polar solute and you tried to combine it with a nonpolar solvent, it would not dissolve. So a nonpolar solute will not dissolve in a nonpolar solvent, and vice versa. I ran out of room. All right, so this is what we mean by like dissolves like. Polar will dissolve in polar, nonpolar will dissolve in nonpolar, but the two don't mix. All right? And maybe we should remind ourselves real quick, what the heck do I mean by polar and nonpolar? All right? So polar quite simply means that you have a molecule where there's an unequal distribution of electrons within that molecule, right? So polar means unequal distribution of electrons. All right, so a good example of a polar molecule would be HF. All right, if we sort of looked at where the electrons were living in this molecule here, we would see that a whole bunch of electron density sits on that fluorine, and the hydrogen doesn't have much electron density at all, right? So there's an unequal distribution of electrons. Part of this molecule has a bunch of electrons. The other part is left relatively electron deficient. And what do we know about electrons and their charge? Holy hell. What is the charge of an electron? -1. Excellent. So if we have this unequal distribution of electrons here, we have a whole bunch of negative charge sitting on one end of this molecule, and that leaves the other end partially positive charged. All right, so this is what it means to be polar, is to have this unequal distribution of electrons. Some electrons live in one part, giving it this partial negative charge, and they're absent from another part, giving it this partial positive charge. Okay, this little fancy symbol here, this lowercase delta, this means a partial, in this case, negative charge. Okay? All right, so we're going to sort of explore this, come back to this idea of like dissolves like here in a second, but now we got to talk about what are called intermolecular interactions. All right? Okay? And that is a big, ugly, scary word, but let's just pick this apart real quick. Intermolecular, that means the intermolecular interactions, that means the interactions between neighboring molecules, right? So we have this solution that has, 10 to the 23 different molecules floating around. What are the interactions between neighboring molecules, right? So that's what we mean by intermolecular. Okay, so now we're going to learn about a few different types of intermolecular interactions here, the type of interactions that neighboring molecules have with one another. And what we're going to do is we're going to introduce them from the weakest type to the strongest type. Okay? So our weakest form of intermolecular interaction are what are called dispersion forces. Okay? Dispersion forces are the weakest of all the intermolecular interactions. Okay? These are the interactions between the surfaces of neighboring molecules. And all molecules are three-dimensional, right? They're super teeny tiny small, but they're these three-dimensional objects, so all molecules have surface areas. The interactions between the surface areas of neighboring molecules we call dispersion forces. Okay? So these are this force of interaction. All molecules have them, but they're very, very weak. All right? Importantly, we also want to note about these dispersion forces here. Non-polar molecules only have dispersion forces. So we're going to learn about a few different types of intermolecular interactions that are stronger than dispersion forces, right? But if you're a non-polar molecule, the only type of interaction that you have are these dispersion forces here. So non-polar molecules only have dispersion forces. All right, and since we're sort of talking about nonpolar molecules, let's also make a note here that CH bonds are nonpolar. Okay? All right, so these are our weakest intermolecular interaction, these dispersion forces that just arise because I got these two 3D objects. They have surfaces. Those surfaces are going to interact with one another, right? But they do so very weakly. So now we have some stronger forces here. Our next level up is what are called dipole-dipole interactions. Okay? These are stronger than dispersion forces. But not all molecules have dipole interactions. What type of molecules don't have these? Because they only have dispersion, the nonpolar, right? So this is then the next level up, but this is only found in polar molecules. Okay? So let's go back to our example here of HF. That's actually a bad example. Okay, another example will be this molecule here. This is formaldehyde. I don't know if you guys have ever taken a biology course where you did any dissection, but you would have worked with this extremely stinky compound here, formaldehyde. This is the structure of that molecule. Okay? And this is another example of a polar molecule. This oxygen here has a bunch of electron density sitting on it, leaving it with a partial negative charge. This carbon over here is left relatively electron deficient and thus has a partial positive charge. Okay? This is what we call a dipole in this molecule here. When one portion of the molecule has partial negative charge, the other portion has partial positive charge, that's what's called a dipole. Right? And these are dipole-dipole interactions. So if we take a polar molecule like formaldehyde, it can interact with a neighboring molecule of formaldehyde through these dipole-dipole interactions, where the partial negative end of one molecule is talking to the partial positive end of its neighbor. Right? What do we know about opposite charges? They attract one another. We have this portion of a molecule that's partially negatively charged. It's going to interact fairly strongly with the portion of a neighboring molecule that has a partial positive charge. Okay? So this is this dipole-dipole interaction. Okay, the partial positive end of one molecule interacting with the partial negative end of its neighbor. Okay? So now importantly, how did I know that this molecule right here was polar or that HF was polar, right? How can I spot when I have a polar molecule? Okay? So this goes back to this concept of electronegativity. And I know everybody did nothing but study chemistry all summer long, but let's review electronegativity so we can make sure to sort of understand what we're talking about here. For that, we want to look at a periodic table. So let me find one. I got one around here somewhere. Okay, ignore all this. So, electronegativity, strictly speaking, if we're going to define it here, this is an element ability to pull electron density in a covalent bond. Okay? So, you learned about different types of bonding. Covalent bonding, you learned, was the sharing of electrons between two atoms. Hopefully that word sharing is kind of synonymous in your mind with covalent bonding. Right? And sharing sounds like it's this nice, neat, like gentle experience going down. Really, those atoms are involved in this epic tug-of-war battle for those electrons, right? Both of those atoms are holding on to those electrons, and they're kind of in like this tug-of-war over that pair of electrons that's bonding them together, all right? It turns out that certain elements are way better at tug-of-war than other elements, and the tug-of-war champion is fluorine. Okay, the most electronegative element is fluorine. If you are in a bond with fluorine, it has pulled all that electron density from that bond onto itself. Okay, and the closer you are to fluorine on the periodic table, the more electronegative you are. So everything trends towards that tug-of-war champion fluorine. Okay? So then how can we spot that we have a polar bond? Right, we said that our HF, this was a polar bond. Polar bonds will occur between elements of differing electronegativity. Okay? So, a carbon-oxygen bond, is that going to be polar? Are those two elements of differing electronegativity? Yes, right? Oxygen's much closer to fluorine than carbon is, so the oxygen in these bonds is pulling that electron density away from the carbon. What if I have a carbon-carbon bond? Is that going to be a polar bond? No, they're the same element, right? One can't be better at pulling electron density than the other. Okay? And then importantly, what about a carbon-hydrogen bond? Remember, these are the ones that we say are always nonpolar. Okay? Organic, there are a lot of molecules out there that exist only of carbons and hydrogens. It's what's called organic molecules, so we'll see a few examples of these. But yes, they are nonpolar if all they have is carbons and hydrogens. Cool. All right. Next level up is what we call a hydrogen bond. Okay? And a hydrogen bond is actually just another example of a dipole-dipole interaction, but using a specific combination of atoms. Okay? So this is just, again, an interaction between polar molecules, a dipole-dipole interaction. All right, but specifically when those molecules contain one of three bonds. It's got to be one of these three bonds to be a hydrogen bonding molecule. Oxygen, hydrogen, nitrogen, hydrogen, and fluorine and hydrogen. All those very electronegative elements paired with hydrogen. So these are the only three types of bonds that can engage in that next level up strength of dipole-dipole interaction, which we give its own special name, hydrogen bonding. Okay? So if we just want to look real quick, it's again going to look very similar to our dipole-dipole interactions. Like the classic example of a molecule that exhibits hydrogen bonding would be water. Right? So if we take a water molecule, it's again got that polar bond, so it's got a partial negative charge on the oxygen and a partial positive charge on the hydrogen. And so if we have a neighboring water molecule, the partial negative end of one will align itself with the partial positive end of the other. Okay, but again, the interactions, that dipole-dipole interaction is taking place between one of those special something in hydrogen bonds, oxygen and hydrogen, right? So again, we would call this, these are both dipole-dipole interactions. This is dipole-dipole because it's carbon-oxygen. That wasn't one of our three special. And then this one is that next level up in terms of strength of interaction, which we give its own special name, hydrogen bonding. Okay? Our last intermolecular interaction here, and the strongest of all of these forces that we've discussed, is an ion dipole interaction. Okay? So we talked about how the partial positive end of one molecule likes to line itself up with the partial negative end of the other molecule, right? The only thing better is if instead of having a partial negative charge, you have a full-blown negative charge or a full-blown positive charge, right? We call those ions. So, again, this is our strongest of all of our intermolecular interactions. And if we see here, we have this sodium ion, right? It's an ion because it's got that net positive charge associated with it. And what we see pictured here are all these water molecules. The oxygen is pictured in red, the hydrogen's pictured in white, and you can see that all of these oxygens have turned around so that their oxygen butts are all aligned on that positive charge, right? The partial negative end of that water molecule is interacting very strongly with that net positive charge. Okay? The basis of all of these polar interactions here is just that opposites attract, right? The idea that negative charges are attracted to positive charges. Okay? And then again, if you're non-polar, you don't have any unequal distribution of electrons. The only thing you have is the surface areas of your two molecules interacting. And again, that's the weakest type of intermolecular interaction that you can have. Okay? So our ion dipole, if we just want to make note here, this is a charged ion interacting with the dipole of neighboring molecules. Cool? All right, so first thing we want to be able to do with this before we sort of move on, we're going to sort of tie this into this like dissolves like concept, right? We introduced that and then we beelined it and started talking about intermolecular interactions. We'll tie these two together, all right? But first thing that we want to be able to do is if I give you the structure of a molecule, you should be able to tell me what the strongest intermolecular interaction that they have are, okay? Now, again, all of them have dispersion forces, right? But what's the strongest? Is there anything stronger than that? Is there a dipole-dipole interaction, or is there hydrogen bonding? Okay? So I'm going to put down a few molecules, and you're going to tell me what the strongest type of intermolecular force is in those molecules. All right, so for this first molecule here, this thing's called ammonia. What are the strongest intermolecular interactions that would be present between neighboring ammonia molecules? So this one would be hydrogen bonding. Okay, and how can I spy that? Because it has one of those three types of bonds that can hydrogen bond, right? Remember, we made this list here. Oxygen, hydrogen, nitrogen, hydrogen, and fluorine and hydrogen, right? If you're on that list, you can hydrogen bond. So in this case, we had a nitrogen-hydrogen bond, so this can hydrogen bond. I know I just said hydrogen bond like 1,000 times. Okay. What about this one here? What does this molecule have? Does it have hydrogen bonding? No, right? Because I do have a hydrogen, but it's attached to a carbon. And remember, we said that those bonds were nonpolar. Okay? But then what's the strongest type of force in this molecule? Dipole-dipole. Because sulfur is quite close to fluorine, carbon is a few tiles away, so I have this bond of differing electronegativity, right? Here's my partial negative end, here's my partial positive end. So this can dipole-dipole interact. All right, and what about this molecule here? So this has dispersion forces. This is a nonpolar molecule. It consists only of carbons and hydrogens. Okay? And then lastly, I actually got to complete this because would be the interaction between these two molecules here. What is the strongest interaction that would take place between water and this thing right here? All right, so if you ever see that net charge, a naked charge on there, that's going to be the strongest forces, those ion dipole interactions, right? The ion of one molecule is interacting with the partial positive end, the dipole of its neighbor. Okay? Cool. So what the heck do these intermolecular interactions have to do with making solutions? This like dissolves like business. All right? Well, let's think about this. We're going to do like a thought experiment here. We're going to make a solution. Okay? Here's my solute. And then I got this beaker. With my solvent in there. And I want to combine these to make my solution, where I have my solute molecules homogeneously distributed, homogeneously, all right, so. Right, I got my solute molecules floating around in my solvent to create my solution. Cool? So, in order to create my solution, I'm going to have to first break the interactions between neighboring molecules in my solute. Right? So I got to take my solute and I got to break those intermolecular interactions. All right, so I have my solute, but now they're all separated out here. All of them have been broken apart. Okay? Now, likewise, I'm going to have to do the same thing with my solvent. All right, I got to make room for those solute molecules. So I'm going to take my solvent, and likewise, I have to break those intermolecular interactions between neighboring solvent molecules. Right? I got to make room for those solute molecules. Okay? In order to do this, in order to break those intermolecular interactions, I have to put in energy, right? These things aren't going to want to separate all by themselves, so I'm going to have to put in some energy to separate these molecules, to break those interactions. So these two steps right here, it's okay, we'll get there, all right? Now, both of these things right here, breaking these intermolecular interactions is going to require an input of energy. So these two steps right here require an input of energy. Okay? But now when I create my solution, right, now I have all these interactions broken. When we create our solution, now we're forming new intermolecular interactions. Right? So now I'm going to stick those solute molecules in between two solvents, and they're going to form new intermolecular interactions. Okay? And since we're creating these new interactions, that step will actually release energy, right? There will be an output of energy when those two molecules find one another. Okay? Cool. So, again, we're trying to tie this back to this phrase, like dissolves like. So let's just think about it. Let's take an example of two molecules that would not form a solution together. All right? We're going to combine a nonpolar solute with a polar solvent, our classic water. Okay? And again, this will not create our solution. So let's explore why that is here, based on what we just discussed. What are the strongest intermolecular forces present in this molecule here? Dispersion forces. Am I going to have to put in a lot of energy to break these dispersion forces? No, they're super weak, right? So I'm going to represent that with the height of this arrow here. These dispersion forces are quite weak, so I'm going to have to put input energy to break them, but I'm not going to have to input very much. Okay? So these are our dispersion forces. We're going to input a small amount of energy. Okay? Now I have my solvent, my water molecules. Actually, let's be good. This is my solute. This is my solvent. Again, I got to break those interactions between my solvent molecules. I got to make room for that solute in my solution. What are the strongest type of intermolecular interactions present in my water solvent? Let's look back. What are the strongest intermolecular interactions between neighboring water molecules? Hydrogen bonding, right? Are those strong or weak? Am I going to have to put in a lot of energy or a little bit of energy to break those hydrogen bonds? Kind of a lot, right? They're pretty high up on my strength scale here. So I'm going to have to put in a lot of energy to break those hydrogen bonds. We're going to call them H bonds for short. Okay. So now we said that like dissolves like, so my nonpolar isn't going to dissolve, but let's sort of see why that is here. So now on my solution end, I have this molecule interacting with water here. What's going to be the strongest type of interaction between water and this nonpolar molecule? Can these two hydrogen bond with one another? No, water can hydrogen bond with neighboring water molecules, but there's no hydrogen bonding potential with this C2H6 business here, right? So what's going to be the strongest interaction that we see between water and this nonpolar molecule? What's the only thing that nonpolar molecule can do? Dispersion forces. And like we said, these interactions will release energy, but is it going to release a lot of energy or just a little bit of energy? Just a tiny bit of energy, right? So I will get a release of energy, but a release of a small amount of energy. All right, because again, these are just dispersion forces. Okay, so the bottom line is it is not worth it for water to make room for this nonpolar solute. It would have to break some very strong interactions to make room for these very weak interactions. It is just energetically a loser, right? You got to put in way more energy than you're going to get out when this solution forms, right? So why do nonpolar molecules not mix with polar molecules? Why is it that only like dissolves like? Because you have to put in too much energy and you don't get back very much, right? Your return on investment energy-wise is not good, right? So why does like dissolve like? Again, just going back to that phrase. Because it requires, or let's actually say, why does like not dissolve unlike? Quite simply because you input more energy than is released. Okay? We're going to spend a lot of time talking about energy in this class. For right now, what you want to know is from the universe's perspective, it does not let things happen that require this net input of energy. The universe likes outputs of energy, so it's not going to let this thing occur. Again, it's an energetic loser. Okay? All right, and we'll explore this concept a little bit more when we pick up next class here. But one more thing that we want to sort of introduce, this other concept, okay? So kind of from that perspective, if we take something like this molecule here, and this molecule here, these two will form a solution together. Right? We have hydrogen bonding on one molecule. It can hydrogen bond with its neighbor here. So in this case, these two will indeed form a solution. Okay? But water can actually hydrogen bond with itself twice. It's got two of these, right? One hydrogen bond here and one here. Okay? So why is it worth it for water to then interact with this neighboring molecule here? There's sort of another force at work here called entropy. And this is perhaps the most bizarre concept in all of chemistry, but it turns out to be a really important force The universe loves disorder. Okay? There is this constant, what's called entropic push in the universe. Nothing is allowed to happen unless it increases the entropy of the universe. And entropy is kind of like a synonymous with just disorder, right? So solutions are just inherently more disordered than a very organized solute where all those molecules are lined up next to each other, in a solvent that's very uniform. So any sort of a mixture is entropically favorable. Okay? And this is this really weird concept. I remember learning it in general chemistry and being like, they have to be lying to me. I'm going to get to advanced chemistry and I'm going to realize that this is actually more, whatever. No, I swear, thinking about it as like this energetic push towards disorder, that is still how I understand entropy. And it's so weird, but the bottom line is that the universe loves disorder. Okay? And we will talk a little bit more about entropy as we go on here. This is just a good thing to kind of keep in mind. Any sort of a mixture will be entropically favorable. It's just a more disordered state. Okay? But we will sort of explore this concept a little further. Again, I don't have my watch on. I'm going to end things a little bit early, and then we're going to have a presenter sort of come via Zoom and introduce that deconstructed research project to you a little bit and have you guys take that initial survey. Cool?